want to dive a bit deeper into, let's say, the mechanisms of how it actually works, and there's a theoretical aspect at the end that we may do if time allows us. Now, as a general, very general introduction, a quantum computer is just a computer, so it's a physical device that can perform computation. It's almost like if we have inputs and we want certain outputs, the process of controlling the inputs to give us desired outputs is computing, and we do it with algorithms in general. A quantum computer is unique in that it uses the concepts of quantum mechanics to do this, and we'll see how, inshallah. Now.
Okay. So, what we are going to touch on is, we'll start with the motivation, both from the theoretical point of view that started with Feynman, and from the hardware and physical need in the industry. And then we will go to the theory. We'll talk about the quantum properties that is used in the quantum computers, such as entanglement, superposition, Pauli gates, etc. We will also talk about the data representation and some of the constraints in the qubits, the hardware and the physical realization of the qubits, as well as the software and the programming language for the quantum computers. And finally, we'll finish up with the quantum hype and just talk about how it's glorified somehow. So, to start with, just as a brief history of computers, computers or calculations started with the tools, the physical manual tools, then went on to the mechanical computers, or known as analog computers, and then digital computers, and now is the quantum computers. After this whole presentation is over, I will just give some brief comparison between these three, especially analog, digital, and quantum computers.
Just one curious question. Anybody has used this rule to do the calculation ruler? You have used it at KFUPM, by the way.
I think the vernier caliber.
When I came here, no, not the caliber. It's a calculator, by the way, that ruler. Yeah, you do the calculation with it. It was used in KFUPM when I came here in 1989. See the development things of a human brain.
Okay. So, the motivation, or the theoretical motivation, started with Feynman in late 1970s. He thought about simulating some physical properties. So when we talk about simulating an electron, so an electron has a spin up or a spin down. When you talk about two electrons, there are four possibilities: both spin up, both spin down, and the alternation between the two. When you talk about 10 electrons, that number of probabilities jumps high to over 1,000. So Feynman thought that if you want to simulate quantum systems, you need a quantum computer, as is shown in this quote here, that shows his personality actually. So that's in the late 1970s. In 1982, his paper, he published his paper Simulating Physics with Computers, and he actually postulated, or some might say he's the father of quantum computers, which I don't condone much, but he postulated that you need a quantum computer in order to simulate and actually deal with quantum systems. And then in 1985, David Deutsch came up with the idea of quantum Turing machines, which is kind of a realization of quantum computers, but the quantum or quantum conducting circuits took over the Turing machine, and it is now the dominant in the field. Moving on a little bit of further years on, Peter Shor started the quantum algorithm, which beneficials from the powers of quantum computers in order to factorize big numbers in the split second.
And if I may, I want to add something to this. Here it's factorization, but this is a misconception, and we'll talk about it in the end, inshallah, about the quantum hype. Quantum computers aren't good for everything, and this is a key differentiation. They're good for factorization, but they're not good for multiplication. For example, if I say 3 times 5, what? 15. Okay, but with the quantum computer, because there's a probabilistic distribution, if this is the probability and these are the numbers, what we'll get is, like, let's say small spikes, a spike at 15, and then small, let's say, probability of different numbers. This is not good, and especially when we have very efficient classical algorithms for this. But with factorization, because usually with factorization we deal with prime numbers, especially in cryptography, there's a common scheme, I think it's called the RSA scheme, which most banks and government agencies use. This is why it's dangerous, cybersecurity-wise, because it's good for factorization, which involves a lot of complexity, etc. But with multiplication, it's not efficient. So this is just, let's say, a side note. Quantum computers are good, but not necessarily for everything.
Yeah, and since you mentioned the security risk for factorization and decryption, as the quantum technologies improve, also a new field of quantum technology emerges, which is quantum encryption. We will not go into details about it. It's a very we will be branching out, but it's a fun read if you want to. So this was for the physical need of a quantum computer. Yeah, and if you want to simulate entangled qubits, you need 2 to the power n of bits. So you can think of the powerful comparison in between the classical and quantum computers. As for the physical or industry need of quantum computers, Moore's law says that the transistors will keep on getting smaller and smaller. In 2020, we reached 5 nanometers. We are nearing the units of Armstrong, which is like the radius of the atom. So as the transistors get smaller and smaller, the quantum effect come in the picture, so that the signals can tunnel through between the wires, and this will corrupt the signal. This will affect the readout. This will affect transmitting the signal. So this raises a very big need for quantum computers in order to avoid this issue. So one big quantum properties that quantum computers rely on is the superposition. The main reason in the qubits is that so a physical qubit is either 0 or 1. 0 or 1. But whereas a quantum or a qubit can be a possibility or a probability between the two. So it's like here, it's A of 0 and plus B of 1, whereas where the amplitudes give the probabilities in the two cases. So the 0 here, so the 0 is just basically a matrix of 2 elements. And we will see this used in the Pauli gates when Umar talks about it. So as for the entanglement, as Hussein did a good job today, it's the ability of quantum systems to exhibit correlations between states within a superposition. So what does that mean? That means if two electrons or 2 photons are correlated, measuring one particle of them affects the state of the other. So if you measure, if two electrons are entangled in an opposite state, if you measure one to be spin up, you know without needing to measure the other, it's going to be spin down. So how do you reduce entangled states? For photons, it's kind of a simpler way than electrons. You can shoot these photons through a polarizer. If it's going to be a vertical polarizer, it's going to give you a plus or minus state, and then if you pass these photons through a horizontal polarizer, it's going to give you a diagonal state, which is a probability between a plus or minus. So when I'm talking about the plus or minus, as in the block sphere, you know that, yeah. So this is plus and minus. Sorry, this is 1 and 0, and this is plus and minus. So when you talk, when there is a diagonal electron or a photon that is diagonalized in the after producing, you shoot one photon through the polarizers, and you produce 2 photons with a entangled state. So back to the entanglement. This is how you produce the entanglement. And go on. Yeah. As for the qubit representations, Yeah, this is what I mean. No, for that. Yeah, I think we went over that. See, so the bits are 0 and 1. The qubits are probability between the two. You can go to
Yeah, so I want to add on what my friend Saleh just said. We know in linear algebra that we basically expand our system on a basis set almost. We can treat the axes, these three-dimensional axes, as these basis sets. In 3 dimensions, we have, let's say, y, z, and x. Okay. Our qubits, because with classical bits we have 0 and 1. Generally, we treat, this is a block sphere. We treat photons or electrons, or let's say our qubit, on the z-axis as 0 and 1. So this can be a 1, for example. This can be a 0. This is just a convention. And because our state is normalized, it's always going to be on the surface of the block sphere. However, sometimes, and there are 2 reasons for this. The first is because sometimes we have errors, and so we resort to using other axes. That's why we go sometimes to the x-axis and the y-axis. And another times, we want to use superposition, which we'll talk about the superposition, applying it on a quantum computer. And so sometimes we go to the x-axis, and we have a plus state and a minus state. A plus is just, let's see, it's like this. And a minus is same thing with a minus 1. It's a very commonly used state. They're related to the Bell states as well. We don't really use the Y, but it's related with the phase flip. And so with the polygates, we know that the X is it's like this. It takes 1 into 0, 0 into 1. The Y is, if I'm not mistaken, it's like this. So there's a phase flip when it comes to the Y. And so this 0 and 1 is not the same as this 0 and 1. This 0 and 1 is in the x-axis, yes, and this is in the y. So that's why we see it here. It's almost like from left to right. This is coming towards us. And with the z, it's 0, 1, 0, 0, negative 1. So with 0 stays as 0, and 1 becomes negative 1. And we can see it here. These are really important to computation. Arguably the most important part of quantum mechanics that we apply to quantum computing. And actually, most people specialize in computer science and computer engineering and even electrical engineering. Most of them who major in or start to do some sort of hardware, they always focus on this. Our algorithms are based on this as well. So this is a really important concept. It's very basic for someone who has studied quantum mechanics, but it's an important factor to consider, let's say.
So basically, it's the eigenstates of sigma z, sigma x, sigma y.
Yes. Yeah. And with the Hartmann gate, it's a special gate, which a lot of times they call it the superposition gate. It takes 0 into the plus state, and the minus, the 1, sorry, into the minus. These superposition states. It flips it like this. So it's from let's say a qubit on a z state to somewhere in between them. Now, one thing to consider is it's always on the surface of the block sphere because the state is normalized. If it's not normalized and without this factor, it would be, let's say, poking out almost. Yeah. Yeah, I think this. Okay, now we're going to talk a little bit about the physical qubits because. Quantum computing before was just theory, and there were many people skeptical about it. But because of the rapid development in the field, there has been some sort of applications. It began with usually chemistry and simulating chemical molecules and let's say small-scale chemical problems, and then it expanded to finance. And now people are generalizing it to optimization problems with supply chain and basically anything with some sort of optimization constraints. And so many governments are actually spending billions now on quantum computing. China just launched a multi-billion-dollar quantum computer. In Saudi here, there's some movement as well. So as a result of it, consulting groups have become interested in, let's say, where it will take us. And week I read a report by BCG, if I'm not mistaken, one of the biggest consulting groups in the world, saying that there are about 80% of jobs are on hardware, and only 20% in the theory and in the software, and it's expected to grow. The hardware is expected to grow even further. So yeah, it's just something about the importance of the physical side of quantum computing.
So basically, what you need to for a quantum computer to work is for the qubit is any two-level system, any quantum two-level system that you can manipulate into two-state zeros and one. We're going to see some of it. So we have the topological qubit, which it kind of benefits from the differences in the topological of the matters, and we also have some of the NMR, which the nuclear spin of atoms. It mainly it relies on the idea of radio frequency cosine pulses in the nuclear spins. We're passing by these very quickly because we're going to focus mainly on the superconducting qubits, which we will expand upon. The ion trap qubits are also postulated as the possible qubits, physical realization. We also have the optical cavity qubits. And finally, before we introduce the superconducting qubits, let's just talk a little bit about superconductivity. So, superconductivity is basically when you have two electrons that make up what's called the Cooper pair. This Cooper pair turns these electrons from fermions into bosons. It makes the electrons act like bosons, more like bosons, as in. So two electrons cannot stay in the same state at once. They have to adhere by Pauli exclusion principle. But if you can cool down the conducting matter or the sample you have, if you cool it enough up to 8 Kelvin or even 9.7 Kelvin, you can kind of make the environment. You can prepare it for that, so that the electrons can get paired and move in together in a coherent way, without the need. So they basically can stay in the ground state without needing to adhere by Pauli exclusion principle.
Because what happens is that there is an intermediate interaction between the electrons, which will make the electron trapped in a down state, which is called the Cooper pair state. Okay, and then of course there will be a whole transition of large number of electrons to be in that situation. So they are not anymore. They are bound. These electrons, they are bound. They are correlated by the interaction. They are bound. They behave like what you call boson. So in that case, they are bosonic compound particles. They are not electron compound particles, and they can go immediately to the ground state. That's exactly what happened to transition and superconducting state, which is called critical temperature.
Yeah. So in non-superconductive metals, as you cool down the temperature, the resistance does not go to zero. It gets lowered down. It gets lowered down. As for the superconductor, there is a critical temperature that when you reach it, whatever is beyond it, there is absolutely zero resistance. It's not an approximation. It's not just 0.000 something. It's absolutely zero resistance in the superconductive metals. Here we see the iron has the 8 Kelvin temperature as the critical temperature, whereas the niobium has 9.7, which is why it's preferred to the industry so that it can be reached easier. So,
as a result of this superconducting phenomena, one common application is the Josephson junction. The idea of the Josephson junction actually came, let's say, serendipitously. It came just by luck, by chance. Josephson, he was trying to put a superconductor and an insulator between them, and just lowered the temperature to see what would happen. And he noticed some interesting stuff. Now, just as a side note, this insulator is sometimes replaced with a non-superconducting metal, or a constraint, a physical barrier. But usually we use inductors. And the most important thing is that the I, the current in the sample, becomes IC, IC sine of phi. This phi is the phase difference between the two electrons in the previous slide. The two electrons in the Cooper pair. These two electrons. Okay, and the let's see. Okay, usually the V equals h over 2e d phi over dt. I don't really care about the equations as much as the fact that V and I aren't constant; they change, and they're associated with the phase. That's the most important thing. And as a result of this, one very common application which we need, and we can almost say the entire quantum computing enterprise is based on, nonlinear inductors. And why I say this is because superconductivity has been known for a long time, or relatively long time. And so fabrication of superconducting devices is well known in IBM and Intel especially. And so when the quantum computing idea first came about, they instantaneously applied it to, or tried to apply it on their systems. So they have already fabrication labs, they have the whole setup ready almost. And so they did it on a quantum computer. They applied quantum computing on this superconducting, let's say, scale, or on this idea. It worked magnificently, and then that is what made people interested in it. It showed that it's possible. Without this idea, we may have never had quantum computing.
So, so what's the difference between a linear component in the circuit and the non-linear, as in the dissociation junction? The linear is basically just gives you a equally spaced energy levels. It has the same frequencies between all of the levels. So when you go from state 0 to state 1, it has the same frequency between if you go from state 2 to state 3. As for the nonlinear component in the circuit, it just transforms the oscillator into an anharmonic oscillator, as in that transitioning from the state 0 to 1 is not at all the same as going from 1 to 2 or 2 to 3 and so on. So,
and if I may add, this makes our system a two-level system, a two-qubit system. Because it's a computer at the end of the day. We want it to have only two, let's say, two parts, two segments. Because we control the superconducting qubit with microwave frequency, we need this change in the frequency, right? Okay, this isn't as important for us physics majors, but it's just magnificent as an idea, so that's why I wanted to bring rise to it. There's a guy called Stephen Gavin in Yale. He works on circuit QED, quantum electrodynamics. This picture shows a thing called cavity quantum electrodynamics, which is basically when you have an atom or an electron. Usually it's on the atom scale. We can use the we can see it as the spin of the photons, however you want to view it. What I want to let's say pay attention to is this is on the atom scale. This genius tried to correlate this with circuits, macroscopic objects, almost like a similar idea to a Jodorowsky junction. It's a macro quantum mechanical phenomenon. Usually with quantum mechanics we deal with nanoscale objects at largest. This is very, very, very large, respectively. So he correlated these two things together, and then from this we were able to give circuits to use them as our superconducting qubits, rather than on the very small. Because larger objects, let's say, they're easier to deal with, they're easier to manufacture. In terms of decoherence, which is a common issue in quantum mechanics, it's easier when we have larger devices. It's easier to insulate the systems, so there's less decoherence. It's called Stephen Gavin, if anyone's interested.
Okay. Just to expand upon the idea of a macroscopic realization of quantum properties, what we mean is that in this example, it's going to be that the quantum properties that happens in the microscopic world will appear in the current that we can measure and we can sense in the macroscopic world. Just about that. So now for superconducting qubit, our most important component, The superconducting qubit is just the physical realization of a quantum two-level system to simulate the qubits that we need in for the quantum computers to work. What are we looking at here? We are looking at resonators, and we have here the qubit, which is most probably a Josephson junction. What is happening here is that the resonators read out and they take in and out the information from the qubit as they mediate the communication between us, the users, and the qubit itself. And I just wanted to note that one of them. So why is quantum computing now is difficult? What's most hindering us from going further in the field is the noise. So okay, look at this. All of this is just a big refrigerator. All of the qubits are here in the lowest place of all of this picture. Everything is here to cool down the qubits in order to reach the superconductivity critical temperature. So we have two constraints when we deal with the qubits. We want to isolate the qubit from the outside world so that it does not react with the other qubits, does not get influenced by external aspects or external influence. But we also do need to communicate with it. We do need to read it. We do need to encode information in it. So these two constraints are kind of conflicting. When you cannot go with one and neglect the other, because it will just go to ruin. So, okay. Yeah. IBM is one of the most pioneering companies in this field. They have their own quantum computer, and actually they have this online platform which is called Qiskit. It is it's a treasure. It has a textbook of step by step. It has prerequisites of scientific from the physics side and the computer science side. It's a very comprehensive textbook that is free and available online. They also have they can give you access to a quantum computer. They can give you access to stay in a line and just put your code into a quantum computer and get the result. This actually reminds me I don't know where exactly, but in the early histories of classical computers, people in big universities used to reserve their line in coding. And in the computer room, they needed to have a reservation, they needed to stand in line, they needed to have some time in order to code and use the computers. As in now, when you try to code or program with a quantum computer, it will give you a wait time in order to reach your code and have it executed. This just makes you think if that was the case in classical computers like 30, 40 years ago, and that's the case now in quantum computers, where will we go further in quantum computers? When will we reach what we reach now in classical computers?
This is an example of a quantum circuit. Now, I'm not interested in what it means or honestly the output. I'm not interested. Why we put this here is for two reasons. Firstly, this exists. It's an amazing tool. I don't remember the last time I went and to read a paper, a scientific paper on a quantum circuit without Qiskit being mentioned in one way or another. And this is what it looks like. This is just to familiarize ourselves with it. We can divide this into, let's say, three parts. The first part is the classical part, which is the, let's say, the wires. This is just a barrier for visual aid. This doesn't really have any meaning. This symbol is a measurement qubit. Now, we know in quantum mechanics that when we make a measurement, the wave function collapses. And this is a quantum system. And so when we want to measure these qubits and then modify them later on, what we do is we introduce ancillary qubits, which are almost like additional qubits that we initialize to 0 at the beginning, and then we make the measurements, classical measurements, on these classical qubits, and then these quantum qubits we can use to modify these classical qubits. Let me explain further. We have gates. Okay, we have X gates, Y gates, Z gates, and we usually use X, Z, and H gates. H being the Hadamard gate for superposition, X and Z the normal X and Z gates. We want to use these for any sort of computation, to implement an algorithm of some sorts. However, if we measure this directly, for example, we want this to be 1 and 0. If we measure this, it will collapse entirely. And so what we do is this, we almost like project this onto these states. Because we know that there's a no cloning theorem, which means that we can't copy a state. And so what we do is we implement a controlled gates. A controlled gates basically works if it's 1 and doesn't work if it's 1, if it's 0. So if I erase these. Okay, so for example, a controlled X gate would be this if it's 1, and it's a 4 by 4 matrix. I think it would be 1 0 0 1. Think like this. Yeah. So if it's 1, if the input is 1, it would be if the input is 0, sorry, it would stay as it is. So if, for example, if this cube is 0, Q2 would not be changed here. If Q0 is 1, this would flip. And so we know the state of this without measuring it directly. And then we do the same here. This is a controlled X gate. And we have controlled Hadamard gates and controlled Z gates, but usually when we use controlled X gates. This is almost like a shortcut or a way to bypass this no cloning theorem. And it's used in error correction as well, because like Saleh mentioned earlier, we have a common problem in quantum computers, which is the error as a result of the noise and the decoherence. And so there's one common, let's say, type of error is the bit flip, where 0 becomes 1. We also have phase flip, where it flips, let's say, along the z-axis or the y-axis. But one way to detect the bit flip is this. Sorry,
we're just gonna go ahead and skip some part because time is running out. Okay, you can go.
Quantum computers are amazing. They're awesome. They have the
what does it mean, the word high?
Sounds like the الموضة trend الموضة.
Okay.
Yeah. So it's a lot of times it's exaggerated. People think that it will just automatically take over the world, will break all sorts of encryption, like the RSA, for example. It's an essential part of pretty much any high-level security system, but there are other algorithms in place.
What is the size of RSA? Do you remember? Anybody remember the size of Can?
For example, it can help in simulating quantum chemistry problems. We can use this for optimization, but we still got some time. And so usually in the quantum computing world, we're torn between two things. There are some people who think that it's the best thing in humanity and it will solve all problems, it will cure cancer. And there are other people who are very, very skeptical. Some professors here in the university as well. And they're like, oh, it's just hype, it won't get anywhere. And so the best thing to do, even if you're not interested in it, is to have an open mind, to where you understand the possible applications of it, how you can contribute in one way or other, without maybe thinking that it will somehow take over science and finish humanity. That's
okay. Before we finish up, that's the last thing. I'm just gonna give you it's a perspective on how does the quantum computer differ from classical computers, and I'm gonna use the kind of analogous when you look at the clock. So there are numerical clock and there are the clock with the عقارب الساعة. It's a continuous state space, where the digital is just discrete of steps. These two differ in that the input is in the analog, the input is continuous. In the digital, the input is binary, it's either 0 or 1. In the quantum, the input, it's continuous, but it's controlled, discretized. As for the output space, which is the possible states, in the analog it's still continuous, like the clock. In the digital, it's still binary, and in the quantum, as it was continuous but discretized, it's now binary. As when you measure a when you measure a qubit, it's either 0 or 1. It's one of the two. It's not both. One major difference is that how can you expect the results or the outcomes? Both of these you can expect. You can, if you have the data, if you have all of your program, just like the program, you can actually expect the outcome, but it's just easier to have the computer do it. For the quantum computer, you cannot expect what could the outcome be because it's all based on probabilities. And the state after the measurement, the quantum state will absolutely collapse. You cannot rebuild it, you cannot clone it again. As for the digital and analog, you can remake it again. There's one more. Okay, that's enough.
As a final note, I think we ran out of time.
Thank you very much. Shukran, ya shabab. One thing is that I don't know if you have to have the aggressivity in anything you want to do in this life. And for example, this topic, we have one excellent student who is working on it. Have you ever contacted him?
Yeah. We actually working on a project with
Ahmed Hajar?
Hajar, not so much with Al-Ghadir mostly.
Ghadir is in UK.